Hi everyone. I wanted to mention that I'm presenting this work on behalf of my former student Libing Zeng, who couldn't be here because of visa issues. Let me start with the goal. Given a 3D face model and a target age, our goal is to reconstruct the 3D face model at that target age while preserving the identity of the individual. And we would like to be able to increase the age or decrease the age, like shown in this case, to 20 years old. And in our work, we use a 3D model as the input, as opposed to like simpler configuration like a single image, because we focus on production-ready reaging. And we assume that the 3D model can be obtained, for example, by capturing multi-view images of the subject and then fitting a 3D representation like 3D Gaussian splatting, which is what we use in our work. Now, this problem, 3D face reaging, is relatively underexplored, but I'm going to discuss relevant work in 2D face reaging and then general scene editing, 3D scene editing. So on 2D face reaging, a large number of methods propose to invert an input image into the latent space of a GAN or a diffusion model, and then perform reaging through latent editing. But the inversion process is not perfect, therefore there's going to be some identity loss in this process. Li et al., in contrast to these approaches, proposes to train a diffusion model on reaging data pairs. And because of that, they can preserve the identity of individuals during reaging. But they train a diffusion model from scratch, and because of computational complexity, they use a smaller model, and therefore they can only handle low resolution images. France similarly trains a model on reaging data pairs, but they use a simpler UNet model, and therefore they can handle high resolution images. Now, the problem with all of these methods is that they are not directly applicable to 3D reaging. I'm going to use Fran as a representative example to show you this effect. So you can see the reaged images, and they are of high quality, but if we look closely, we see that the age-related features, which are the wrinkles, are not 3D consistent. And this is going to cause problem when we are doing 3D reaging. Now, on 3D general scene editing, there are lots of recent work that they are mostly diffusion-based, and they follow a similar pipeline. Given a 3D model of the scene, they render multi-view images from that model. And then given an editing text prompt, they use a editing diffusion model, like, for example, instruct pix to pix, to edit the images, which these images in turn are used to optimize a new 3D model. Now, to enforce multi-view consistency, they either have some constraints in the feature space of the diffusion model, or they employ some tricks during optimization. And these methods can produce wonderful results with general editing text prompts, like turn him into a Hulk. But when we use them for reaging, the results are not visually pleasing. And this is because of two main issues. First, the general editing network that they use is not designed for reaging. To address this problem, we introduced diff reaging, which is a diffusion-based model, which is highly tuned for the reaging task. Now, even if we use our diff reaging with their optimization pipeline, the results still are not going to be satisfactory. I want you to note that the target age in this case is 80 years old, but the edited 3D model looks much younger than that. And the reason is that the multi-view constraints that they have are not sufficient. And strict multi-view consistency is crucial when we are dealing with reaging, because the wrinkles and other age-related features are really fine scale. So as a result, these approaches produce inconsistent wrinkles, and these are going to be overblurred, which is giving the appearance of a much younger individual. Now, to address this problem, we enforce strict multi-view consistency directly in the image space. And as you can see, we can produce results that are highly detailed, and they have appropriate target age. All right, I'm going to explain these two components first by discussing diff reaging. So this is a diffusion-based 2D reaging model. And the choice of diffusion model is not just because it's powerful, which it is, but it's also critical for our multi-view consistent reaging, which I'm going to discuss later. So in contrast to the previous approach on reaging, which trains the diffusion model from scratch, we propose to fine-tune an existing editing model, in our case, instruct pix2pix, on reaging training data. And this is to use basically the strong priors that are already encoded in the original model. Now, to be able to do this fine-tuning, we need reaging training data consisting of input and target images and the corresponding target age. To construct this data set, we use SAM, a GAN-based reaging model, which given an input image, it can produce reage images at different ages. Now, this SAM model, it works based on diffusion inversion, and as I mentioned before, because of diffusion inversion not being perfect, there's going to be identity inconsistency between the input and reaged images. However, as shown in a couple of previous approaches as well, we use the same observation. The identity of the reaged images are between themselves consistent. So in order to construct our data set, we randomly sample a pair of images and then put them together to form our triplet. Now with this training data, we can fine-tune a diffusion model to obtain our diff reaging. At inference, diff reaging takes a target age, a source or input image, and then it progressively denoises pure noise to obtain the reaged image. Okay, now with diff reaging explained, let's see how we can utilize that to do multi-view consistent reaging. And for our system, we also follow the pipeline of existing general 3D scene editing. Specifically, we render a grid of cameras. Then we use our proposed multi-view consistent reaging, which integrates diff reaging in it, to generate 3D consistent reaged images. And these are in turn used to optimize a new 3D model. Now here, the key idea of multi-view consistent reaging is to reage only the central or frontal view, which we call it a pivot view, and maximally reuse information from that image to reconstruct the other reage views. This component has 3 modules. I'm going to explain it by first discussing the flow and warping module. So here, as I explained, we first use diff reaging to reage only the pivot view, the center view. And then our goal here is to warp this image using optical flow to reconstruct its neighboring views. I'm going to use this image to explain the process, but the rest of the views can be constructed in a similar way. Okay, the key challenge here is that the optical flow should ideally be computed between the reaged pivot and neighboring views. However, the reaged neighboring view is exactly the thing that we want to compute, so it's unavailable at this time. Our solution is to compute optical flow on the current rendered pivot and neighboring views. And the idea here is that as the 3D model during optimization progresses towards a reaged model, the optical flow also iteratively gets improved. Okay, now we can obtain a warped image using this strategy, but there's going to be some missing content because of occlusion. In the next stage, we fill in this information with our mass diff reaging. So here our goal is to fill in the missing or occluded regions using our diff reaging model with reaging content in a way that those details, like wrinkles and other details, are consistent with the already existing data in the warped image. And to do this, we adapt diff reaging to mass diff reaging, which uses the iterative denoising process in diffusion models. Specifically, at every time step of diffusion process, we add noise to the warped image according to that time schedule at that step to obtain a noisy warped image. And then we combine this noisy warp image with the denoised image at that step using the occlusion mask to obtain the final denoised image at that time step. This image xt is then passed to the next step to repeat the same process. And the high-level idea here, which was introduced a couple of years ago for different applications, is that by injecting the warped image at every step of the diffusion process, we force the diffusion model to reconstruct the missing regions in a way that they are consistent with the existing content in the image. All right, now if we do the flow and warping and mass diff reaging to reconstruct all the neighboring views from the input image, we have the risk of reconstructing the overlapping regions with inconsistent data. So to address this problem, we propose a very simple center-out reaging. Just briefly explaining this, starting from the pivot view, we reage it. Then we perform warping to reconstruct the immediate 4 neighbors. Then we perform mass diff reaging to fill in the missing region. And we repeat this process of flow and warping and mass diff reaging to iteratively propagate the information outward. And with this, we are basically reducing the chance of reconstructing the overlapping regions independently, which would hurt the 3D reconstruction. Okay, now that we have the reaged images, we can do the optimization. And this component is very similar. We use the basic 3DGS optimization with densification and pruning. The only minor change that we make is in the loss to reinforce the pivot. Now, these two components that we have, the reaging and optimization, we alternate between them. I briefly hint at that. As the optimization progresses and the 3D model moves towards the ReAge representation, we want the optical flow to also improve, to further improve the reaged images, and that further improves the optimization. Now let's see some results first on 2D and then on 3D phase reaging. We do 2D comparisons against fading, a diffusion-based model, which works on diffusion inversion, and then Fran, which is a feed-forward model using unit. Here's a comparison against fading, and because of diffusion inversion, as I explained before, fading produces results that have inconsistent identity with the input image. However, our result produces individuals that have consistent identity, and they are consistent with the target age in this case. Here now we see a comparison against Fran. This is a feed-forward method. Both ours and Fran can preserve the identity of the individual. But if you look closely, we see that Fran has difficulty removing all the wrinkles from the original input, which should do in this case because the target age is 20 years old. In contrast, our method removes all the wrinkles from the original input and adds tiny wrinkles closer to the eye, which are more realistic. And this is mainly because we are using a more powerful diffusion model as opposed to a unit. Here we have some numerical comparisons. We sample 1,000 unseen images from FFHQ. We reage each one of these to target ages ranging from 10 to 80 years old. And we compute age error to see how consistent the reaged image is with the target age, and ID score to measure the consistency of the identity of the individual in the reaged image versus input. And you can see that ours produces across the board in all ages and for identity better results than existing methods for 2D reaging. Now let's see some 3D comparisons. Here we compare against instruct Gaussian to Gaussian and Gaussian editor. The plus here means that we are replacing the general editing diffusion model with our diff reaging. So we are helping the approaches. In the paper, we have comparison against the original model as well, which the results are significantly worse. Here again, as I showed at the beginning of the talk, instruct Gaussian to Gaussian overblurs some of those fine wrinkles and produces an appearance that is younger than the target age, which in this case is 80 years old. And even in this case, you can see it's slightly even appearing younger than the input 3D model. Gaussian editor similarly overblurs the wrinkles because they produce inconsistent target images. In contrast, ours is highly detailed and kind of matches the target age of 80 years old. We also have numerical comparisons here. We use 10 subjects, each with 4 different facial expression. Each of these 3D models are re-aged to target ages ranging from 10 to 80. And because the age error is computed on the 2D images, we render 30 views for each subject and compute the error on those images. And here again, you can see that ours has the lowest error. Particularly, you can see that on 80, the gap is even larger because they overblur the wrinkles and the appearance is much younger than 80 years old. In contrast, ours produces consistent age target. All right, let's conclude the talk and discuss some limitations. We addressed on the explored task of 3D face re-aging. As opposed to training a diffusion model from scratch, we repurpose a pre-trained editing model. And for 3D consistency, we enforce strict multi-view consistency directly in the image domain. And we demonstrate better results in both 2D and 3D face re-aging. Now, our approach has several limitations. I list just 2 of them over here. First, if the face is occluded, our approach is going to have difficulty. The 2D diffusion model is going to have difficulty re-aging them properly. And this is because we don't have such cases in our training data set. Also, as you saw in the previous talk for leaf, there is also biophysical models for skin aging, which we don't incorporate them into our re-aging model. In the future, it would be interesting to incorporate them. Thank you for listening, and I'll do my best to answer the questions.
Yeah, so we have time for a couple of questions. I see one hand here.
So one thing off the bat that I could see could be an issue is what about the effect of lifestyle choices on the person, like as they age? Like, are they a smoker, or do they spend time in sunlight without sunscreen, or do they spend time indoors?
That's an excellent question. So this field of re-aging, that's one of the major challenges. In all of these work, the training data set that we have is also synthetic. These are generated based on some GAM model, based on exploring the latent space. So whatever that gives you, we are using for training data. So that's an open research question, basically using exact physical data and incorporating those kind of external factor into the model. So that's an open research question. Yeah, we don't handle that.
I guess just a little remark that I think one way to go is to take like people and with like, for example, seniors nowadays, and take like old photos of them and restore the old photos to look modern, have that as an intermediate step, and then that's the way you could get actual training data.
Yes, and that's going to be a huge task of getting those data, collecting the data set, and then correcting for like the camera model that was 70 years ago, for example, changing that to match the recent cameras, lighting and different effects, and also gathering those kind of information, external information that you talked about. Yeah. And that would help for training such a model. Yeah.
Over at the back.
Thanks for the nice talk. What I was wondering about is, if I understand it correctly, you don't take into account aging of hair. And some of the previous models, maybe I've just seen it incorrectly in the results section, they did that. So is that the future work, or how would you propose to do that?
Yeah, so that's something that we didn't do. We specifically, yes, you're correct, we focused on the face. And the reason for this was that in production, like the hair and other stuff, they can easily adapt them by putting on a wig on the actor or actress. So that's easier for the artist to model. The face is the difficult part. But incorporating those kind of effects, yeah, that would be a future work. Yeah.
Thanks.
Okay, one more question and then we move on. Yeah.
Okay.
Yeah, Nima, thanks for the talk. Lovely. There is this stream of papers now that just say if you want to have consistency for diffusion models, all that you need to do is to make the noise consistent. So you just swap that on around. So you do something slightly in between, you inject some new noise, but you warp the intermediate result around. Have you tried, like, I mean, this go with the flow, or how I warped your noise, these things, maybe you cite, or did you try that? Is this promise any justified they make?
I mean, the work was with Netflix, go with the flow is with them. I don't remember if we tried, but there was discussion of that, and it for like tiny details of wrinkles and stuff, that's not sufficient. So in this case, and you have to consider that those noise models are in the latent space, which is heavily compressed, low resolution. The wrinkles are finer than that resolution. So there are challenges when we are dealing with re-aging. Maybe with general scene editing, as I showed, those solutions would be sufficient, but there are specific challenging to this re-aging because these tiny details have a significant impact on the perception of the age.
Yeah, I believe the answer, but there's this trend now that more modern diffusion models might not work in latent space anymore, and then maybe this consideration changes, so we'll see what the future brings.
A lot of things that we do, if we can get the image diffusion models to be computationally feasible, maybe we don't need to do those stuff because some of them are designed because we are working with this tiny latent space.
We don't know yet. Thank you very much.
All right, thanks the presenter again.
Thank you.